Thanks for joining me for MTI's Whiteboard Wednesdays. I'm Dan Adams. Today we're talking about direct drive, linear, inertia, and low force friction welding, and the applications that are best suited for each technology. Today we're going to talk about different traditional friction welding applications and whether or not they're best suited for direct drive, inertia, or linear, and we'll probably throw in some low force too. But instead of me talking about this, we're going to ask for a little class participation. Here is a traditional high-volume automotive application for rotary friction welding. This is an axle flange where I'm welding a tube to this flange. The question is, which rotary friction welding technology do you think is best? Traditionally, this is a direct drive friction welding application. And I can put as much heat as I want to in here. Maybe these are hardenable steels, and again, I need to control the cooling rate. And then after welding, I probably turn this flash off with a 2-axis flash removal tool. The challenge is I can't remove the ID flash, which hurts us from a fatigue performance perspective. Now, while this is a traditional direct drive application, MTI looks at this slightly differently. We could use inertia friction welding on this application, and now my cycle time is faster. And then instead of turning the flash off, I shear the flash off, and I'm getting another cycle time benefit from that perspective. But I'd challenge you to think about this with respect to a low force application. Instead of getting the flash curl, I get a flash bulge. So now it's much easier to remove on the OD, and I don't have to remove it on the ID, and I don't get hurt with respect to fatigue performance. So this is a great low force application. Here is a high volume electrical connector made out of copper and aluminum, and these are welded all over the world. It's a round part, so there's a clue. Which technology should I use? Because it's round, you're going to default right to direct drive or inertia. Because it's a global component, most people do direct drive friction welding. It's really easy to do with the direct drive technology. But because it's so high volume, you might be able to shave a couple seconds of cycle time if you use inertia friction welding. So we do this at MTI with inertia. But because it's a bimetallic, I challenge you to think about using low force friction welding, because now I can bias the heat towards the copper and try to get some copper upset as opposed to just upsetting all the material out of the aluminum. And now I might get a slightly stronger weld as a result of using low force. While we're talking about copper to aluminum, now I have a non-round component that I want to weld. It's still a bimetallic copper to aluminum, but I'm not going to rotate one of the pieces. So which technology should I use? Clearly, because it's not round, you're going to be thinking about linear friction welding. And with linear friction welding, we can weld copper to aluminum with the same quality that we can in rotary friction welding. But again, bimetallic. As a result of it being a bimetallic, I should think about low force so that I can bias the heat towards the more difficult to weld alloy, and therefore this is a great candidate again for low force friction welding. Here is the classic hydraulic cylinder rod. I'm welding a clevis or an eye to a bar, and that bar may be pre-chromed. I got a round component. Which technology am I using? The classic approach to welding a hydraulic cylinder rod is direct drive, but I will say if you're welding a mild steel component, that you could probably use inertia and get this done with a lower cycle time. When I'm using a hardenable steel, I want to be able to extend my weld time, get a lot of heat in so that the cooling rate is controlled and I'm not forming martensite. I get great fatigue performance. The challenge with that is that longer weld time means more upset. And now I get this big flash curl that I have to remove using a 2-axis flash tool. So the flash removal and the additional weld time is a cycle time penalty, but again, I'm controlling the cooling rate to get the performance that I need. So the predominant technology is direct drive, but I would encourage you to think about low force. One, because of the flash morphology, getting a bulge instead of a curl, and the ability to control the cooling rate with preheat or post-heat so that I'm not having to have really long weld times and I can weld more parts per minute. Here is a specialized component. Now this one has been machined after welding. This is a 350 millimeter diameter barrel, and we're making welds between each of these sections. So it's a multi-part assembly. It is a large diameter, thin wall tube that we're welding. It's round, so which technology would you use? Now, if we're thinking about this from a titanium perspective, you might say, okay, direct drive, I can make this weld. The reality is when I'm doing titanium and Inconel on one machine, the titanium can be done with direct drive, but the Inconel cannot because of drive motor torque limitation. So this is a classic inertia welding application. Anytime that I think about large diameter, thin wall tubes, we should start thinking about inertia, especially in aerospace materials. But I challenge you to think about this with respect to low force. I have to machine this flash off after welding. So if I have a flash curl in here, getting a turning tool in between these is really difficult. If I can make a low upset weld and have a little bit of bulge there, I don't necessarily have to remove it. So now low force becomes a very competitive application, and my machine sizes are much smaller. So low force is definitely something that should be considered for aerospace materials in these large diameter thin wall tubes. Here is another global high volume automotive application. This is a turbocharger wheel where we're taking an Inconel casting, a nickel superalloy, and welding it to a steel shaft. It's a round component, so you choose which technology do you think is best. Now, direct drive can make these welds very well, and they're done all over the globe. The challenge with direct drive is if I get the timing of my speed coming down and my forge force going up incorrect, I can have a quality issue. So there's a little bit of art associated with doing that, but it can lead to bad parts. So MTI uses the inertia welding process because it's really easy. There is no trick. It's very straightforward. So our standard approach to turbocharger wheels is inertia welding. But because it's a bimetallic, you should stop and think that low force would be a great application because I can bias the heat towards the Inconel, and I can get a really fast weld. Therefore, low force would be a great alternative to pursue with respect to turbocharger wheels. Here is another high volume automotive application. This is an axle, but this time we're welding a spindle to the tube. This is a 150 millimeter diameter component, and it's done in hardenable steels. It's round. Which technology would you use? The predominant technology for this is direct drive, and it's done with a double-ended machine. We're welding two spindles on simultaneously. It's also a hardenable steel, so I have to put a bunch of heat into the component to make sure that I'm controlling the cooling rate in order to avoid martensite. But again, I can't get in to remove the ID flash. Therefore, the design of the component has to take into account that there's going to be a mechanical notch there with respect to fatigue performance. This is actually a part that we welded using low force friction welding. And you can see that the flash formation here is significantly smaller than what would come off of a direct drive friction welder. And you can see on the ID side that there is no need to try to remove this because it's so low. The fatigue performance of this low force weld was equal to, if not exceeding, the direct drive. My cycle time was lower, and I made this on a 10-ton machine instead of a 125-ton machine. So in terms of being able to hold concentricity, part deflections, all the tolerances that you want out of this component are better with low force, and I get the same fatigue performance because the ID flash morphology, and I don't have to remove the OD flash if I can live with it because it's just a bulge. Low force is a clear winner. We've talked about several traditional friction welding applications, and we've gone through whether it's best suited for direct drive, inertia, linear, or low force. If you're keeping score at home, you probably realize that low force is the clear winner on many of these applications because we've been able to take aspects of each of these technologies and build it into the low force. But we can build any of these systems for you, and we look at your application and decide what is best for that component, and we'll choose a technology that is best suited for you. Thank you for joining us for this episode of MTI's Whiteboard Wednesdays. For more information on this topic or other friction welding solutions, please visit our website at mtiwelding.com.